Maybe it's so slowly, this connection, maybe this connection is slowly as calculation time. I need maybe more time to save data as to calculate. And now I have only 1 minute, it was quickly. Okay. And now we have to answer the last question. Breaks our part or not? So, okay. So this was the simulation. It's 10 minutes, not 11, 1 minute quickly, and I think it's so slowly. Maybe in your was your simulation quickly or no? Did you try? Yours was quickly. Okay, but this question you can answer in your practical work. You have to do it. Yes, in your practical work you have to show difference between direct and iterative. It will be. But in lectures, you will see it was much more quickly. Okay, but I don't know why. It's normal. It was always a little bit quickly with direct method, and of course with these basis functions. Okay. Okay. Okay, it was quickly. Yes, you see it 90 minutes and 8 minutes and 6 and then 7 and 6 minutes. So, and with a big program, yes, big task, you see 45 hours. If I say which parts, for example, this press stress parts quadratic, the other parts linear, then I can save 20 hours, and if I say direct, I can save 10 hours more. Yes, and with this theory, I can save a lot of time. And now the last question: breaks our part or not? So this is the main questions, and this is our target. Yes, target. How can we say breaks part or not? We have two possibilities. First possibility is the best solution, what's possible, and second, what we are using if we don't have best solution. So best solution is SN line. So what is it? SN line. The best solution. Normally it's difficult to find. It's better to make measurement. It's SN line. So for free it's not so easy to find. Or maybe the company who produce parts for you can give you this SN line. So SN line is in German Wörterlinie. It's a Wörterlinie. Yes, what is SN curve? It's the best way. The best way to say breaks or not breaks. To have this SN line. Okay, maybe I have builders. Okay. Okay, let's show you what is it. But normally we don't have SN line. Yes, it's not possible to find on the internet, and it's easy to make measurements. Okay, or to ask a customer SN line stress. In German it's called Wörterlinie. Fatigue stress, yes, okay. What it means, this SN line, I'll open one picture and you will see what it means. Then it's very easy for simulation. Okay, SN lines means it means we have measurement. What is the measurement? It's easy. We take part and makes 1 million, for example, loads. Yes, or we make loads before part breaks. Yes, for example, we make 1000 megapascal. Yes, it's always force. Yes, I say, for example, 100 Newton. Stress is force divided area. Yes, it means I say 100 Newton. It's 1000 megapascal. And I make this load 0, 100, 0, 100, 0, 100. And then after, for example, here, after 1000 loads, part is broken. So then I have point. 1000 loads, my part can live with 1000 megapascal. Then I take next part, makes, for example, 900 megapascal. and then I make load 0, 900, 0, 900, and now after, for example, 100,000 loads is broken. Yes? So then I take one part, makes, for example, 500 megapascal, and then I did 10 million times, and it's not broken. Yes, and then I say, okay, more than 10 million times I cannot do. It's not possible. It means this is my limit. Okay, and then I have this SN line. This line tell me stress depends on cycles. So easy. Yes, and then I do my simulation. My customer told me 1 million. I show, okay, 1 million. I need 800 megapascal. I do my simulation. I see 600 megapascal. It means it's broken. Yes, it means after 100,000 loads it is broken. So, and then, for example, if I need 800, then I try to do my simulations that it works with 900, for example. Yes, with safety. So easy strategy, but the problem, we don't have this line. We need to break many parts to have this line. Yes, or material. Who makes material? Yes, this company. He give us sometimes SN lines. Then it's easy. Easiest way. Yes. But we have other way. This line is not possible. Yes, it's measurement. And the people, yes, for many hours found other solution. Goodman, Soderberg, these all methods use this ANSYS also. Yes, but don't make it in your report. Here in ANSYS, for example, you can also find fatigue tool, and here you can find all these words what I showed you. Yes, look, mean stress theory, and we have also here Goodman, Gerber, and so on. It's second way, not so good way, like no, not so good. It's a good way, but it's one possible way to without a measurement. So this guy Goodman, Soderberg found that they made many tests, and they understood that. That if you make this line, we are using always this Goodman method. So it means one side is endurance limit, it's stress at break, and other side is other way. Yes, this is endurance limit. It means how many stress my part can get. So, and it means this point is half of my stressed break, half of my stressed break. So, and here I have other point is stressed break. So, and then they make a lot of measurement and understood that if my stress under this line, then it's safe. If my stress further this line, then it's not safe. So this line means safety factor 1. So you can read a lot of information. You can make this line with a formula or points to show. But at the end, we are using this formula. So in the end, so this formula is safety factor with this theory, Goodman theory in this point. This is the most. It's conservative. It's with safety. It's good. So this Goodman theory told us if I have two calculations. With zero load, with maximum load, yes, then I can use this equation, and this equation my safety factor. So it means safety for it's not broken, but safety for what? For 1 million, for 10 millions, yes, for 1,000. It's like safety for 10 million loads, yes. So if I have 1 here, then it's safety. If I have 0.9, it's not safety. If I have 1.1, it's safety, but not exactly how many times. Yes, so maybe 1 million times. Then everybody wants those big customers. Then if we use this theory, then our charge is 1.5, 50% more safety. It means if I make this Goodman safety factor, I want to see 1.5. Then 1 is safety, 1.5 means it has to be real safety. Yes, so. This is our target, 1.5, 1.4, so 1.3 sometimes. For example, our part is broken, yes, in reality, after 500,000 lots. And target was 600,000 lots, yes. And simulation told this 500 million lots is 1.5 2. Yes, and if we do something optimization, we see 1.3, it means I'm better, and now it has to work. So it's like better or not so better. So okay, but target 1.5 is normally safety. So and it's easy. We need 2 points only. Maximum stress. In ANSYS with this tool you can show this safety factor in all points, but it works not so easy. Normally it's not important. We need only maximum place. So we need only this point. With load, without load, yes? We have these loads, 0 max, 0 max, 0 max. So what we see that maximum load times step 2, 229, yes? Stress. So maximum stress 229, and minimum stress is by time 1. I have press stress always, yes? I need exactly in same place with maximum stress, yes? Exactly in this point I need stress by minimum. So then I can show here with probe, it's about 26 megapascal. So it means my problem place, my place with maximum stress, it's always between 25 megapascal and 290 megapascal, yes? So this is my task. Is it safety or not if my tensile stress between 26 and 290 load changed always? So, and then we have here, okay, maybe not so, okay, no, it's okay, yes. We see the safety factor means I use one stress at break, yes, 660 ultimate range, then my safety is half of stress at break. Yes, safety, like experiments showed that about half of break. Yes, if my parts breaks with 600, then safety is 300. So it's like theory. So then I write my material property 660, half of 660, and here is my metal stress and amplitude. Yes, my stress change between here how many? It's okay, 39, so looks about 39, and here 307. So what it means, my middle stress, yes, is summa divided 2, yes, it's my middle, and my amplitude is maximum minus middle stress. So if I do it, then I have middle stress 180, amplitude 183, yes, so. Yes, and if I use now this safety factor, I have 1.4 safety. So, and these points I can write here. Yes, like here one amplitude, yeah, Wechselspanne and amplitude are 150. Here point and I don't know 130, and then you see point is underlined. But this graphical is not important. This equation is only important. So this equation tells us, is it safety or not? So, okay. Normally we are using this Goodman safety factor. Every software uses this Goodman safety factor. It means we calculate it, and then we say the program makes now show me safety factor with step 1 second and step 2 seconds. Yes, and then program calculated in every node this equation. So easy. And maximum, of course, in the maximum stress. So. And so easy is it, yes? So I make simulation, I find minimum without pressure with pressure, yes? Okay, press stress is separately, press stress I have always. This pressure I have 0 max, 0 max. It means I have in this place 4300 megapascal. And the question, is it safety? I use safety factor. Goodman theory, Goodman told us 1 is safety if I use this equation. Then I try to be more safety, as Goodman told, 1.5, and if I have this, then I say it's safety. So easy. But the most easy, of course, is SN line. It's really simple. Yes, I calculate 500. I show 500 means 200,000 loads. So, and then I can say, is it safe or not? Yes, this is the easiest way. And this way is like if my limit 300, so I can say it. Yes, if my limit 300, then it's safe. But if it's limit not 300, then it's not safe, yes? Okay. So easy is the story about mechanical simulation. And you know everything now about simulation. Yes, you know we did this nonlinear simulation. We saw the program controlled. It's not so best solution. We can do quickly our simulations. And now you know everything about structural mechanical simulation. Advantage, yes, ANSYS finite element method. We can calculate everything. Disadvantage, it's system of linear equation. Needs a lot of time. And we need theoretic knowledge to be quickly, yes, how FEM works. Where do we need fine meshing? In the places where we need solution. Other places we don't need fine meshing. For nonlinear simulation, we need these all things, yes, material properties, recalculations, and this RSX knowledge deflection on, yes, these all parameters, true stress, true strain, and then we can do contacts, yes. So, what is a good mesh? Good mesh is beautiful mesh, yes. Better is to do the sweep method, yes, to do hexa mesh, but it's need a lot of manual work, yes, to create hexa mesh. So, but it costs our simulation will be weekly. Okay, and now I want to do flow simulation. You will see that you understand sometimes, yes, that you understand that what is really important by flow simulation. Yes, sometimes you can see a really interesting example, but you will understand today why it's one simulation bad and other not so bad. It's only maybe two things that important to understand by flow simulation, and we will try to create geometry for the next lecture. And next lecture we will calculate this flow simulation. So, okay. Okay, please save in Felix file. In Felix you can find file geometry for flow simulation. Okay, I'm delete Felix. Okay. In Felix you can find file. Ich habe auch. Moment, I did a copy. It's called like CFD something. And we need to create first geometry for our simulation. Okay. So, okay, it's called how it called? I don't have. In Felix, did you find? No. Yes. I didn't say it. Oh, okay, I have to go.
It's in the folder. German 2009.
Yes, can you see?
Yeah.
No, it's other. It's last year or German version. It was other example. Now I have other example. And the new example on the Felix I saved. It was a little bit. It was different. Now it's other example. So okay. Flow simulation. Very important. Okay. And you can find this file. Yes, geometry for CFD simulation, CFD. So. Okay, CFD, and how we can do the simulation now? It's same story with drag and drop. We have now a problem. ANSYS has problems. ANSYS has two softwares for flow simulation, CFX and Fluent, and it's not really clear. You can make everything with both software. Yes, we used CFX all times, and many people use CFX now, and Fluent was not so good or not so, I don't know. But the last time they tried to do this Fluent more functional, and it's not so clear. But normally mostly people uses CFX now, and we are using also CFX more, and with drag and drop you can add this file CFX, but you can do all things with both software. So CFX is much more like in Fluent. It's much more easy maybe to do simple simulations. It's only click clack and then it works. Here you will see it works not so easy, but it's like you can make more things. You will see more control, more. It's better for me. Okay, today. Okay, we are using CFX, and in YouTube, if you look, it's a lot of CFX users videos. Okay, first we need to import geometry. Yes, we will not do now geometry. We have three maybe important things in fluid simulation. First thing is geometry. So please open geometry, and in your practical work you have to do flow simulation. Yes, flow simulation is simple. It's only two questions. Yes, I say inlet is pressure, then result is flow, or inlet is flow, result is pressure. Yes, or flow force. So it means I have normally two tasks: pressure inlet, flow outlet, or other way. Yes. So, and normally we are searching flow forces to see or to calculate it together with magnetic simulation and to see how much flow force. Yes, or for example, customer told us with 2 bar pressure delta he want to see 6 liters per minute flow. So, okay, and first we need to import geometry. So we are opening our space claim tool, and then like somebody did in SolidWorks, yes, in CAD software, geometry, and we want only to import the geometry. And it works really simple. Here we can say where is it? Assembly file, and then we can add file. All files, and we can add our file geometry for CFD step file, and then we have our geometry. So, and with this geometry we can do mechanical simulation, but we want to do flow simulation. So this is our geometry. Okay, this is our valve. Yes, it's like real model. Yes, here is inlet, here is outlet, flow is diesel. Yes, and the question is how much is, or pressure is defined, how much is flow, and how much is flow force. Yes, so depends on position. So, and your in practical work, the question was to do the simulation with 1 millimeter stroke, 1 millimeter position, and first we need, of course, to have design with 1 millimeter opening. So how we can do it? If you push 3 times mouse button here, then you can choose our body, yes, and then we can say we need 1 millimeter stroke. Yes. How we can do it? We can use move function. If you use move and you move left, you see how big is the stroke now. You see that the stroke is 0.5 millimeter. Yes. And then if you move your pin left 0.5 millimeters, then we have 0 now. Yes, 0. And the task is to find to do simulation for 1 millimeter stroke. Yes. Then I can choose again 3 times mouse button, and I can move 1 millimeter right, and then I have 1 millimeter open. So, did you understand? I moved pin half millimeter left, then I have 0 point, and then I moved in other direction 1 millimeter. Then I have 1 millimeter stroke, 1 millimeter opening. And the first thing by flow simulation, what is important, for flow simulation, for mechanical simulation, I need my geometry. For flow simulation, I need geometry of flow. Yes, this is the first main thing. So I need my flow geometry. I need this negative geometry. Yes, I need geometry other. Yes, negative, like negative of my geometry. Yes, I need flow geometry. So this is the main target. First, we need to create flow geometry. How we can do it? For this function, we have. Okay, you can see it in the slides. Yes, I moved left and then right 1 millimeter, and then we need to create negatives. So
Why do you move right now?
the task is to find solution for 1 millimeter stroke. So first we need to create 1 millimeter stroke. So if you make import, if you do import, so I delete it. I'm doing import geometry for say B. So and yes, I want to define 1 millimeter stroke. How I can do it? So first I need to find 0. Where is 0? Then I can move my geometry left 0.4, 9, 0.45, no, 0.5. So now it's 0.5. So, and then I can move back again my geometry. For example, now it's 0 stroke, yes? And now I can again choose my geometry and move, I don't know, 3 millimeter. Then I have 3 millimeter stroke, or 2 millimeter. And task was to find solution for 1 millimeter first in your practical work. Yes. Do you understand? So I choose again 1 millimeter. This is 1 millimeter opening. So. And now I want to do the simulation for this 1 millimeter opening. But the main difference to mechanical is you need geometry of flow. Yes, I don't need this geometry. I need geometry of flow. I need everything but inside. So how I can do it? We did it simple. I create new body. This body is bigger as all bodies, and then I say this new body minus all bodies, and then I have geometry inside. So easy is it? How we can do it? Okay, we did it. We create new body. For example, I choose this face, copy, paste. Then I have new surface. Then I can pull this new surface. No merge. Right mouse button. Not connection. No merge. I move it. I don't know, like here. Yes. I have full bodies inside. And then I can do this body minus all other bodies. Yes, this new solid minus all solids. So, and I can do it in many software. It's the same story with better how it calls with enclosure. Enclosure function is it's like minus for many bodies. So you will find it here. Calls always enclosure here. Okay, we have here other option, but it doesn't work really well. This is the best way enclosure. It was in last software the best way, and now it's also. So enclosure, if I push this button, the program told me select one or more bodies to create enclosure around. Yes, I need to choose my all bodies. Okay, here is like I need to choose all bodies first. Yes, all bodies without my new body. Around these bodies, I will create new body. Yes, like negative. Then I push this button next. Select a solid to use as enclosure shape. Then I use my new body here. You can find in lectures also this. And then I say OK. And then program created me a volume inside. Okay. Inside my valve. So, do you see?
How did you create a new body?
So, I show again. Okay, I created new surface. For example, this side copy paste. This side of body I used make copy paste. Then I have new surface, and then I use this new surface with pull on function to create new body.
How do you select, or how do you create this new surface?
Copy paste. So I click here and then
Okay, got it.
strong C, strong file, and then I have surface. And then pull function, so pull, and then right mouse button, no merge. The program create new body, and then new body. And then with this enclosure function, I can make this. Okay, of course I can also do like so I can also create every part separately, this part minus this part with combine function. But this is the best way, this is an enclosure. So enclosure means I choose, where is it? So prepare enclosure, I choose all bodies around these bodies I want to create new body. So I say all bodies, 4 bodies. So yes, one or more. So my part I can only solid, new solid, I can choose only one. So it means if I see one or more bodies to create enclosure, I choose my all bodies. Then I push here and then I choose one new solid bodies to create enclosure, and then I choose my one bodies, and then program delete it automatically. So, and then I have here new geometry, it's called enclosure. So this is the new geometry. This geometry inside my valve. So, and this is geometry for the simulation. This is the first main thing for the flow simulation. Yes, we need this negative. We need flow geometry, not valve geometry. So, and then with 3 times mouse button, you can choose your new geometry. So, okay, here you can find the lectures. Yes, 1 millimeter stroke. Then we create new body face. Then I pull my face with no merge function, and then I say enclosure. So, and then I have this geometry. So I don't need other. I can delete everything. So I don't need. I can delete really everything. For the simulation, it's not important. So, oh, okay, bad story. I delete too much.
My enclosure was young. Is that the problem?
Bigger? No, we need to edit this geometry after. If you have too big, then you have here maybe, yes.
Yeah.
Volume, but we need to edit this at the end. So first is not problem. So important is that you have all important regions. Yes, important. Here is everything okay. Yes, you see everything is what important inside. Here I have to delete it, of course. Okay. Okay, if I did it, I can delete everything. Okay, everything. I don't need geometry more. So this is my geometry now for the simulation. So, okay. And now, of course, I need to delete everything what I don't need. Yes. Everybody created geometry? Flow geometry? Oh, it's too big. What is it? No, it's okay, yes. Then, umfüllen, genau. And then program asks you, more bodies means many. Many, you have only your bodies. This word many. So, you can choose your bodies. Then you go to the next step and then one body.
your new body, and then you see screen. You see screen.
Then you don't need other geometries. Then you can help your colleague.
You see the enclosure?
No, I don't know what to do with
I don't know.
Is it escape? If you see something there,
After the enclosure, what do you do?
you are in
Encapsulate.
some program.
Enclosure.
So, you can do
Enclosure.
Give it the line. Give it. What is this? Whatever I use inside. Last time my laptop this time it's completely
so 3 times.
left 0.5 8.
You have to copy this.
No, then it is computer, but it is
Control one.
I know I maybe nice. Now 0.50. Then you can move back. How it was 1.
And now we can create this enclosure. Try to do it. And you do it. But lost. Okay, and now I have also small. Okay, now of course you don't need all places small gaps. Yes, small gaps is no flow. So your flow here comes inside. Here inside, here outside, here you don't have velocity, nothing. Yes, it's a stay flow. It's nothing here. Yes, you can delete it without thinking. Yes, small gaps, all small gaps, you have to delete. So, and you will see it also in the lectures here. Yes, I wrote yes, small air gaps, not necessary. Cost many elements, more time, and it's better to delete unnecessary geometry. Here we don't have flow velocity, it's stay flow here, and we can delete it. So how we can do it? Easy with this slice function. Yes, split body, or in German version, how it's called, but this point, we are using only pull, move, combine, and split. So
What should I delete?
Everything except.
it's nothing here. You can calculate, but it costs a lot of elements, yes? It costs now million and elements. For what? Here you don't have velocity, you don't have flow. Flow stay here. Yes, only stay. Nothing. You don't have force from this part or maybe it's not stay. In reality here we have it's closed, yes, in reality. You don't have the flow in reality. So here you have this damping, or how it called. It's closed, and then you don't have flow. So, and you can delete it. Okay, we split body. We can delete it. We can choose this body and then cutter here, and then we can delete everything what we don't need. This three
Where?
with cutter you can delete it. So here, split body. Split body, then you can choose your body, and this function we are using always. And then you can choose face to split here, then escape, and then you divide your geometry. And now you can choose this part and delete it. So we don't need it. So, and then of course you divide now your geometry a little bit. Then of course you can delete this part. Yes, here for example. Also small gap, and here we don't have in reality flow. No, not here, this small gap, yes, for example. It costs a lot of elements, yes. It's not real to calculate, this small gap. It's happened nothing, yes. Our flow come here inside, here outside, and here is nothing, no velocity. It's nothing important for the simulation, and we need to delete it. So, we say again split body here, then split body here, and then we can delete this part. So now it looks better. Yes, now we can combine it again together. Combine, And then we have again one part. And of course, these small things like this one, we also don't need things yet. It's cost a lot of elements,